Good morning, everyone. I would like to start by thanking the organizers for this amazing event and for inviting me. I'm really happy to see so many people interested in changing paradigms in quantum science. And today I'm talking to you a little bit about resource theories in quantum foundations. And I'm not going to talk just about my work, so I'm trying to give an overview of different resource theories that we use here, and in some part of the talk I'll be talking about the work that is not mine, but it's done by some of you that are here in the audience. So if you feel like I'm missing something, or you have anything important to say about your own work that will be presented here, please interrupt me at any time. So in this talk, I would start talking a little bit about the general mathematical structure of a resource theory. And then I will talk a little bit about different resource theories that we have in quantum foundations. So the first one, the most developed one, is the resource theory of entanglement. Then I'll talk a little bit about resource theory of steering. And finally, my own work, resource theory of nonlocality and contextuality. So, a resource theory is a general mathematical framework that helps us to understand some physical property as a resource. And these resource theories, they consist of some main ingredients. So the two main ingredients that we need is a set of objects, and which are the physical entities that may possess this resource, and the free objects, which are the entities that do not have any resource. And we also need to talk about operations, which are transformations that will take me to from one object to another one. And we also need to define what are the set of free operations, which are the operations that can be implemented at no cost. And then we can speak about other things as well. First, quantifiers. We like to quantify things, so we want to know how a quantitative measure of how much resource I have in my object. And of course, I would like to have a relation between quantifiers and practical applications of my resource. And we also can talk about a lot of other issues regarding interconversion of objects, like distillation protocols, conversion rates, catalysts, and this kind of thing. So I will mainly be interested in these three things here, but I'll mention briefly some results that we have on these things here as well. Okay, so the mathematical framework that I will use is based in this paper here. Very nice paper if you're interested in the mathematical aspects of resource theories. You can also see this talk by Tobias Fritz in Natal. And we start by two abstract sets. One is the set of objects, and the second is the set of operations. So transformations that take an object into another object. So one thing that we need from these operations is that they can be composed sequentially. So you have this operation of composing sequentially. And we also need to know how to compose objects. So here I'm using this tensor product notation, but it's not necessarily a tensor product. This object only means that having an object A and an object B is another object of my resource theory. And another thing we need is composition in parallel. So if I have an operation that takes A to B and an operation that takes C to D, then I can talk about the operation that is implementing F here and G here that will take A and C to B and D. And the one more thing that I need is what I call a trivial object, which is the object that represents having nothing. And this is done here in this equation. So if I have an object A and the trivial object is the same thing as having just A. Okay, so I need a lot of technicality on these definitions here, so they have to respect some constraints They are related to the physical meaning of all these operations. So all of these things, plus these extra restrictions, we have a fancy name for it, and it's called a symmetric monoidal category, but you don't have to worry about this name here, unless you're a mathematician. And all we need to know is that we need these main ingredients to build a resource theory, okay? So, after I have all of these objects, the resource theory, the next step and the crucial step is to define what are the free objects and the free operations. So the intuitive idea behind this definition is that the free operations are operations that can be implemented at no cost. They do not create any resource. And the set of free objects are the objects that can be created at no cost. They have zero resource on them. So there are two main ways of defining the set of free operations and the set of free objects. I can start by studying the set of operations and characterizing the set of free operations. So if I do that, I fix the set of free operations. Then, fixing the set of free operations, I can define a free object as an object that can be created from the trivial one by a free operation. But we can also do the opposite. Instead of starting with the free operations, I can start studying the set of objects, and I can characterize the free objects, and then I can define from this one the set of free operations as the set of operations that preserve the set of free objects. Okay, which approach I will use will depend on the resource theory or on the problem I'm studying. So this is generally related to a difficult task one has to perform and the limitations you have in performing this task. And in this talk, I'm considering a more abstract approach, so I will do the following thing. I'll study the set of objects and define the set of free objects, and then I will define the set of free operations as the largest set of operations I can find which preserve the set of free objects. So I'll start defining the free objects first, okay? Now, the next step is to talk about quantifiers. We love to give numbers to things, but before talking about quantifiers, I will talk a little bit more quantifiers in the end of the talk if I have time. But before talking about quantifiers, I would like to stress that quantifiers do not capture everything we need in a resource theory. So when you have a resource theory, we have what we call a pre-order on the set of objects. And we say that A has more resource, or at least as many resources as B, if there is a free operation that takes A to B. This defines what we call a pre-order on this set of objects, which is a way of comparing these objects. But this order is not what we call a total order in general. So there are objects that cannot be compared to one another. If every object can be compared to any other object, we have a total order. So when we have this kind of construction, we can talk about quantifiers, and which is just a function that assigns a non-negative number to all of the objects in such a way that this number is 0 if I have a free object, and this quantifier preserves the pre-order on the set of objects. But these objects, these quantifiers, unless the order is a total order, they do not capture everything, all the information we have here in the pre-order. So whenever we talk about a quantifier, we are losing information on the resource theory. So these quantifiers may be related to practical applications, and then the quantifier may give you information about this practical application, but not on the resource theory itself, unless the order is total. So the pre-order is always more fundamental than quantifiers in the general case. Okay, so other important questions we can address. I'm not going to talk exactly about these things today, but they are important problems. So to identify when objects are equivalent under the free operations, conversion protocols. When can we convert one object into another object? If we cannot convert, can a catalyst help the transformation to be implemented? Can we distill, like, from an object that has a small amount of resource, can we find, using several copies, another object with more resource? Conversion rates. Another question that is important is if there is a resource bit, which is an object from which all other objects can be generated using free operations. Or if there is no resource bit, it means that we have different classes of resources. And we would like also to create quantifiers that are related to practical applications of a resource. Okay? So before I continue, a very, very important example, resource theory of beer. So the objects in this resource theory are glasses of beer. And the trivial object is the empty glass. The free operation is this drinking beer. And the costly operations, the operations that are not free, is filling the glass with more beer because it will cost you money. But if you go in a deeper level, you have to produce beer. And this is a very costly operation. It takes you money, time, and a lot of labor, space, and everything. And this is a very, very important resource theory, but this is not the one we are talking today, or at least now, maybe tonight. So I would like to give you an overview of some resource theories of non-classical correlations that we use in foundations of quantum theory. And of course, they are related to quantum information as well. So if you are interested in very different resource theories in quantum information and quantum science in general, I highly recommend this paper here. It's very nice. It gives a really good overview over these resource theories that we use in quantum. The ones I'm speaking today and some other ones as well. Okay, the resource theory that is most developed in our field is the resource theory of entanglement. And in a resource theory of, I'll talk about bipartite entanglement, but it does not need to be bipartite. But in the resource theory of bipartite entanglement, we have two parties, Alice and Bob, and they have a pair of quantum systems. And the objects in this resource theory are bipartite density matrix, and the free objects are the separable states. And the set of operations is quantum operations, general quantum operations on this density matrix. And the set of free operations, we can think first as the set of all operations that preserve the set of separable states. But this is not a very, very good idea. You can see this talk by De Vincenti in Natal as well. It's a very nice talk if you're interested in, in the relation between these different classes of free operations. So this another set is called the set of separable operations, and they have a really nice mathematical characterization. So we know mathematically how to characterize them. They have the Choi matrices separable, but not necessarily we have a physical implementation for these operations. And the more physical set is the set of local operations and classical communication, but then it's not that easy to characterize mathematically. So we have this dual problem here. So this is the most studied class of free operations for entanglement because of its physical appeal. So a local operation with classical communication is basically like this. So Bob here will implement some operation, quantum operation, any quantum operation he wants to perform in his system, possibly a measurement with different outcomes, whatever. And then he will communicate his procedure to Alice. So he will send her a WhatsApp message with or without fake news. And then she will act on her system based on the information she received from Bob. So this is what we call one round local operation with classical communication. And they can use several rounds of these. Then Alice can communicate to Bob what she did, and we can go on and on. And that's why these operations are not that easy to characterize mathematically. Okay, so using this set of, if you're interested in local operations with classical communication, you should read this. It's a really nice paper as well. So there are many important questions that have already been addressed in a resource theory of entanglement. This check mark here doesn't mean that the field is completely closed, but it means that we have a lot of knowledge on that answers. So we know when two density matrix can be converted using these operations. We know the role of catalyst. You can ask Cristiano over there if you want to know more about this. And we have a lot of distillation protocols. We know how to compute conversion rates. And in the bipartite case, we know that we have a resource bit, but in general, we have different classes. And we also have a huge, huge number of quantifiers with different applications, each of them. I will not talk about quantifiers now, but I'll come back to these later if I have time. Okay. The next thing I would like to comment is the resource theory of steering. So first, let's understand what is steering. So now, Alice and Bob, they still have two correlated systems. And Bob has full access to his system. So he has a quantum state that he can implement any quantum operation he desires. But Alice, she does not have full access to her system anymore. Her system is inside a closed box. She cannot open the box. And this box has a set of input buttons that will decide which measurement will be applied in her system, and a set of outcomes that will give the outcomes of these possible measurements. So that's the only thing she can do, okay? And the correlations between these two systems, they can be witnessed by the following fact. When Alice chooses a measurement X and has an outcome A, the final state of Bob's systems will depend on the measurement and outcome that she gets. And this way, we can witness the correlations between Alice and Bob. So now, this system, it's not going to be described by a density matrix because we don't know what is inside Alice's box. The only thing that she can do is to compute probabilities for measurement and outcomes. So Alice's system, Alice's box, is described by probability distributions of this kind. And depending on the measurements she chooses and the outcome she gets, the state of Bob's systems will be described by this density matrix, okay? So this is the set of objects now. They're called assemblages. And the free objects are the local assemblages. They are the assemblages that can be constructed using only classical correlations. And the resource are the assemblages that are constructed using correlations that are beyond classical correlations. And the operations in general are local operations and classical communication. But here, local operations for Alice are a bit different from the case of entanglement because now Alice cannot open the box and do whatever she wants. She just can pre-process the input of the box and post-processes the output of the box. And the free operations are one round, local operations and classical communications from Bob to Alice. So Bob can apply whatever quantum operation he wants in his system and send the information to Alice. And then she can use a pre-processing box here to pre-process the input of the target box and then post-process the output here using another box. So this is the set of free operations in this kind. So it's not the most general set of operations that will preserve the set of free objects, but this is related to one-sided device-independent key generation. And this is the kind of free operation that will not compromise the protocol. So it's not the entire class of free operations one can think, but it's related to applications of these practical applications of steering. So important questions. Conditions on two objects such that one can be converted to the other. In this paper, they answer these questions for some classes of assemblages, but this is an open question for general assemblages. Distillation protocol. I tried to find distillation protocols for steering, and I've found one master thesis in Rio that addresses this problem, but I couldn't find anything else. So if you know anything about this, please let me know. I also didn't find anything regarding catalysts or conversion rates, but we know that there is no resource bit for the resource theory of steering. It's proven here. And in this case, we have infinitely many different classes of assemblages that cannot be converted into another one. Okay? And we also have quantifiers, but I'll talk about the quantifiers later, as I told you. Okay, so we're moving now to more abstract objects, so from entanglement to steering and now to non-locality. So now both systems are trapped inside boxes that cannot be opened. So both Alice and Bob have boxes that may be correlated, but they cannot open the box and freely do operations on their systems. So the only thing that they can do to describe these boxes is calculate probabilities for choosing measurements here and having outcomes here. So now the descriptions of their systems is given by a probability distribution of having outcome A for Alice's measurement X and outcome B for Bob's measurement Y. And the free objects are the local correlations. They are the correlations that can be created with classical communication, shared randomness. And the operations are global wirings. I will explain later what these things are. And we have two sets of free operations. One is local operations and shared randomness. That is the one I will consider later. But there is another set called wirings and prior to input classical communications. And there are different classes of resource theories and of free operations. And you can see the discussion about the differences among these things in this paper here by Leandro and Rodrigo. So what are these local operations with shared randomness? So the idea here is that this is the target boxes, and now Alice and Bob will do a pre-processing of the inputs of the box, and then they will have a post-processing of the outputs of the box. And these boxes here, they have to be local, and these boxes here, they have to be local as well. So here we have a brief summary of these different types of operations. This is the thing that I just mentioned before, pre-processing and post-processing. This is the target pair of box. So here I have local and local pre- and post-processing. So for general global wirings, the only difference is that these pre- and post-processing, they do not have to be local anymore. So here, Alice only uses information that is on her side. In global wirings, Alice can send some information to Bob, or vice versa. And this is the class of wirings and prior to input classical communication. So Bob can do some pre-processing here. And then they can do a post-processing that is local. But Bob can communicate to Alice something before they use the pre-processing box. So it's a more complicated set of operations that is not included in the global wiring. So there are operations here that are outside this set. But the ones that are most important are the local operations with shared randomness. That is just pre- and post-processing with local boxes. Okay. Conditions on two objects such that one can be converted to the other. Again, we have partial knowledge on these things. And we have distillation protocols. We know how this works. We know a little bit about conversion rates. We know that the existence of resource bits depends on the scenario you're working. So in some scenarios, we have a resource bit, and in other scenarios, you have different classes of non-locality, and we also know a little bit about quantifiers. Okay. Just a minute. I have no idea how much time I've been speaking, but okay. So now I would like to talk a little bit about research theory of contextuality, which is my main line of research. And the objects here, now we're moving to a more abstract than non-locality. And now the thing is that I have only one system inside a box, and I'm looking at correlations between different measurements that I can perform on this system. So I start with a set of measurements in one physical system with a given set of outcomes. And I also have a set of subsets of these measurements here. And these subsets, they are called contexts. And what is the information these contexts have is that they tell us which measurements can be performed jointly. We know that if you have, for example, a quantum system, you cannot perform any measurement you want jointly because there may be incompatible measurements. So these contexts, they're telling us which measurements are compatible and which are not. So now I will use this example here. I have 3 measurements, A, B, and C. And I have 2 contexts, A and B and C. And I can also represent these objects as boxes. So I have my physical system trapped inside this box. And I have this set of inputs which will decide which measurement I perform. And here I have some lights that will turn on telling me which is the outcome of each measurement. And non-locality, mathematically, non-locality can be seen as a special case of this scenario in which I have a physical system that is split in 2 parts, and there is a wall inside of my box telling me which is in Alice's side and which is in Bob's side. And the contexts are basically pairs of measurements, one for Alice and one for Bob. Okay, so my box is characterized by a set of probability distributions, one for each set of buttons I can press, one for each context, and this set of probability distributions is what we call a behavior. And in my example, I have these 2 probability distributions here. These will characterize my box. And the objects that I will be interested in are the non-disturbing behaviors. So what I want is that if 2 contexts overlap, the marginal distributions have to be the same in each context. So in my example, the contexts overlap in measurement B. So no matter how I compute this marginal, using this or this, they have to give the same value. So this is a non-disturbing behavior. And the set of what we call non-contextual or classical behaviors, the ones that you can generate using a classical probability distributions, are the ones for which we have a global probability distribution, which is a distribution over the entire set of measurements, such that the probability for each context can be recovered as a marginal. So again, in my simple example, the non-contextual behaviors are the one for which I can find this global probability distribution here in such a way that these 2 probability distributions from the behavior can be recovered as marginals. Okay, so the set of free operations for a set of free operations for contextuality has been developed in this reference here, and they basically have the following structure. So here is my target box that I want to transform in something else, and I will have here a classical pre-processing box that will pre-process the inputs of the second box. And then I have a classical post-processing box that will post-process the output of this box here, okay? The post-processing can depend on the pre-processing. And then I have this final box with this set of inputs and this set of outputs. And this pre-processing here cannot be totally free. I'll not enter into the details here, but we have some restrictions that we have to impose on this dependence. And the good thing is that we can now calculate the probabilities for the final box. So we have like a parameterization, explicit parameterization for the set of free operations in this case here, okay? So other important questions. So from all of these resource theories that I have talked about so far, the one that is less developed is the resource theory for contextuality. So we still have a lot of work to do regarding this kind of resource theory here. So we have also very partial knowledge on the conditions on two objects such that one can be transformed to the other. We are working on distillation protocols, but we don't have answers to that. Also nothing about conversion rates. And again, for resource bits, we know a little bit. So we know that for some scenarios, we have resource bits. For example, for those familiar with contextuality, the cycle scenarios, we have resource bits, but not in general. And we also have nice quantifiers, and one of these quantifiers I will talk about later is related to practical applications of contextuality, so we have a nice way of quantifying contextuality. Okay, I still have time, right? Okay. So now I would like to talk a little bit about quantifiers. And the reason why I decided to let this for the final part of the talk is that many quantifiers are defined using the special ingredients you have in each resource theory. But many quantifiers, they are just using general properties of these resource theories. So I would like to mention a few quantifiers that are basically the same for all of the resource theories I have been speaking so far. So the first set of quantifiers I would like to present is the set of quantifiers that are based on relative entropy. So we've seen that many of the resource theories I presented to you, they involve probabilities. And relative entropy is a nice way of measuring how different two probability distributions are. So since my objects are created using relative entropy, I can use relative entropy to quantify how different these objects are. So for example, in the case of non-locality and contextuality, using relative entropy, I can create a relative entropy between boxes, which is a way of measuring how different two boxes are. Both in contextuality and non-locality, this works very well. And it's basically looking at the context that will give me the biggest difference between these probabilities distribution here, okay? There is another way of defining this, which is called the uniform relative entropy between boxes. Instead of maximizing over the context, you take the mean over the context. But the second way of defining this will not give a quantifier that is good for this resource theory that I showed, okay? So we also can define a notion of relative entropy between quantum states. It's given by this formula here. So both for boxes and both for quantum systems, I can talk about relative entropy. And now I can use this relative entropy to define a quantifier of resource. In the entanglement, I'll use relative entropy between quantum states. And in non-locality and contextuality, I can talk about relative entropy between boxes, okay? So this is just the minimum relative entropy of my object and the set of free objects. Okay, so these kind of quantifier are studied for these different sets, different kinds of resource theory in these references here. There is also a way of defining a relative entropy for assemblages. I will not go into the details, but this first author is here in the audience, so we can talk about this later. Okay, so now another set of quantifiers based on the geometry of the set of objects. So the first one is what I call resource content. They have different names in different resource theories. I'll talk a little bit about it later. And this quantifier is not special of any resource theory. It can be constructed whenever the sets of objects and free objects are convex. So the only thing that is important here is convexity. So here I'm representing with gray the set of all objects, and here in red the set of free objects. And now giving any object, I can always write this object as a convex combination of a free object and something else, okay? So I'll look at all the ways in which I can write this object in this convex combination, and I'll look for the convex combination that gives me the minimum amount of this thing here, okay? This is a quantifier of the resource that is preserved under any linear transformation I can make on the set of objects, and is defined more formally in this way. And for non-locality, it is called non-local content, or EPR2 decomposition. And for steering, it is called steering weight. And for contextuality, it's called contextual fraction. But they are all the same thing, constructed only based on the convexity of these sets. And this quantifier is really good when you have a practical application of the resource that is linear, because here linearity is the main important thing. For example, for contextuality, in this paper here, there is a relation between contextuality and measurement-based quant computation. And the advantage that you get with contextuality is linear, and hence you can connect the contextual fraction with the how useful your contextual box is in measurement-based quant computation. So this is a really nice thing when you have linearity of your application. And the last thing I would like to say is that we can also have quantifiers based on distance. So it's the same idea that I did with the relative entropy, but now you can replace relative entropy with other distances, mathematical distances on the set of free operation of objects. So here I have the set of all objects. Here I have the set of free objects, and I can quantify the resource in this object here, but by looking at the distance of this object to the set of free objects. And here there are many distances that you can find, and if you choose wisely, this will be a really nice quantifier related to the application you have. So it's the same thing, but now instead of relative entropy, I can use any other distance in the set of objects, okay? And this has been done for entanglement in this reference, and for contextuality and non-locality in these references here. Okay, so with this, I finish what I have to talk to you today. So I would like to give you an idea of what is the resource, the mathematical framework of a resource theory, and also how you can use this mathematical framework to study non-classical correlations that appear in quantum foundations and in quantum information in many cases. So I tried to give you an overview of the objects and free operations we can use in any. So if you want to know a little bit more in the details of all of these things, I'll be here the entire week. You can talk to me later. And also some general quantifiers you can use. And with that, I finish.
Okay, questions? No? Okay, then I can start. I have a question because you talked about a set of free operations, But there can be different ones. I can add all of them. Or
The set of free operations will depend on a lot of things. So what we would like to have is a characterization. Well, for me, in a mathematical way of seeing the thing, I would like to know the entire set of free operations that preserves the set of free objects. But this is a really difficult task in general. So what we do is we have some physical way of defining the set of free operations. And then you see what you can do with that set you can find. So that's what we have here. So that's why we have different sets, because you have different characterizations for them. But for example, in entanglement, the most general set of free operations you can find that preserves the set of separable states, it's not completely free, in the sense that if you have this system here, and if you apply this operation to this system, it is a free operation. But if you add an ancilla, or if it's in a bigger system, then if you see this operation as this operation here, and identity on the rest of the system, it may not be free. So there are a lot of subtleties in the definition of these free operations. And what we do is to try to find a physical way of defining a large set of free operations that will give you freedom to study different things, but you still have a way of applying these operations in a lab or something like this. So, but of course, if you're interested in practical applications, for example, if you're interested in doing this kind of operations in a lab, you will have much more restrictions than just the mathematical ones, because you know the things that you have to use to implement, so you don't have all this freedom. So you can also think about the resource theory with a more restricted set of free operations, depending on what is easy and what is difficult for you to implement.
Thank you. More questions?
Thank you. So when you put up the slide about the difference between the set of free states and putting the contextual fraction on that, you have this connection to the boundary, and the boundary is like the totally contextual area. So you're working on geometrical aspects of contextuality. I haven't looked at your preprint yet, so maybe this is answered in that. But do you have any kind of physical intuition for how many really very contextual states do we get that are like interesting to us computationally? So ones that are close to the boundary versus ones that have only a little bit of contextuality according to the contextual fraction, but maybe are still useful computationally.
Yeah, this is a very important question, and it is related to the fact that these quantifiers do not capture everything. So. Yeah. A quantifier is a very crude way of addressing a resource theory. So, of course, the contextual fraction will not be everything in all applications of contextuality. But the thing that I can say to you is that for this specific application of contextuality in measurement-based quantum computation, contextual fraction is good.
Yeah.
Because if it gives you an upper bound on what you can do with that. But if you change the application, then you don't know anymore. So maybe contextual fraction will be bad, and if you have these objects with very, very little contextual fraction, maybe they are the best ones. Mm-hmm. So, but I don't have like a specific example to give you now.
Well, thank you. That was insightful nonetheless.
Yeah, we can talk about this later.
Thank you.
So you mentioned the fact that resource theory in general is a symmetric monoidal category. I'm not really into resource theory, but I have some notion of category theory from operational probabilistic theories in that context. So I was wondering a very basic question for curiosity. The symmetricity requirement is something that appears to me as mimicking some features of quantum mechanics, quantum theory, and classical theory. I was wondering if it doesn't prevent the application of resource theory to more general theories.
No, I will explain to you why we need symmetry, okay?
Okay, thank you.
It's not working anymore, but okay. Okay. So the monoid, the category thing is here, objects and operations. So these operations will be the arrows between the objects in your category. Now the monoidal thing comes from this thing here. So you have a binary operation that takes you that takes a pair of objects into another object, and the symmetry comes here, because the symmetry is saying that you have a natural isomorphism between A and B and A. And this is because if you have an object A and B, and having B and A should be the same thing. So in general, in these categories that we consider is even more strong, that is not just a natural isomorphism between these two objects, but it's also is in fact an equality between them. So the symmetry comes from the fact that having A and B is the same thing as having B and A. So order is not important here. It's just having an object that representing having the two at the same time. So this does not have anything to do with the physical way of generating the objects. So this would apply to general probability theories as well. Okay?
Maybe one last question. Okay, so let's thank Barbara again.